Okay, I think we're recording. All right, so I'm not here, obviously, in the on campus or anything, and so I'm going to talk a little bit about uh, go through a lecture that is for intended for Tuesday, March 18th. Okay, and we're still in chapter four. What we're trying to do is, again, just to kind of remind everybody. We had spent a lot of time working on streamlines and basically solving problems using the Bernoulli equation in a streamlined format. Now, what we want to do is move away from streamlines and look toward fields, velocity fields, acceleration fields, and so on. And that will allow us a more general approach that we can apply in a broader set of situations where streamlines might not be either applicable or convenient. Okay, so and one of the things we had to account for was the fact that fluids have a very unique, uh, convenient way of being described. It's not like a particle. Again, I use the example of a baseball a lot. It's not a finite collection of points that make up a coherent whole that you follow through space and time. It is you know, fluids are, it's very difficult to identify a specific point, and it makes the equations of motion that result very inconvenient to use. It also, I mean, there are ways of doing that, and there are lots of computational models that are Lagrangian that do follow individual points around and that kind of thing. But computationally, it's a little bit complicated. It's easier to simply stay put in one spot and look at the fluid go by you and just take a look at the properties of the fluid at that point. So that's the Eulerian point of view. So we talked about that sort of coming into this. And so now what we're doing is we're dealing with the fact that velocities are not only functions of time, but they're also functions of space, even in steady flow. So what we then need to do is reevaluate the way we calculate accelerations. And from that, we can then take a look at how we can calculate forces due to fluid flows and so on. So anyway, one of the things we did last time before the break was to take a look at the material derivative, which I'm showing right here. I'm sorry, I'm at home right now, and you might hear my cat or my dog or any one of my dogs or maybe several cats making noise in the background. One's kind of giving me stink eye at the moment because I refuse to stay in my Eulerian point of view long enough for her to come up to me and bite my hand. Anyway, so what we did what we did last time was you looked at material derivatives, looking at the change of velocity as a function of time. And if that velocity was also a function of space. So this is the general way that we did it. And then we wrote it out into component forms for the component. Let's see, x is this way, I guess. Yeah, right. X, y, and then z upward. And then also that would have the component u, v, and w for the component for the velocities lying along those axes. So this would be the component form for the acceleration of a velocity field that was a function of space and time. And it takes into account the translation between those. So let's take a look at an example and see how we can actually evaluate this and what it actually means for us. Okay, so let's say we had a hose has a nozzle on it, And fluid is flowing through this hose at 5 feet per second. That's what it is upstream of the nozzle. And then the nozzle is a length of 2 inches. And downstream of the nozzle, the fluid flies out at 40 feet per second. Okay. But this is steady flow. Steady in the sense that the 5 feet per second has been going into the upstream side of this hose for time immemorial. We don't even know. And then 40 feet per second of fluid flow has been jetting out of the outflow of the nozzle along the same time. So there has been no change in time. So, but what is the acceleration? So let's say we'll just assume that the only thing that really is evident here is flow in the x direction. So our x component of acceleration looks like du dt plus u du dx plus v du dy plus w du dz. Okay. So we want to be able to evaluate that. Well, first of all, it's steady flow. So this is going to go away. Let me write that a little bit neater. Um, there's no flow in the y or z direction. So there's no flow up and down and no flow in and out of the paper, only flow going from left to right. So those are both zero. Now you can make the argument, and the argument has been made, that because the nozzle is getting smaller, that there has to be some kind of flow going in the vertical direction or in the horizontal in and out of the paper direction. We'll just assume that that's small or negligible. So all we have left is this, right? Now, which velocity do we take? Which velocity do we use? We've got two of them here. We've got 5 feet per second and 40 feet per second. So which of these are we going to be able to use here? Well, what we do is we use an average. So 5 feet per second plus 40 feet per second divided by 2 is equal to 22.5 feet per second. You'll see this used commonly. If you've got two very distinct velocities, you don't know which velocity to use, you might just use an average of the two. And so to calculate this du dx, we essentially just have the difference in velocities over the distance, dx. The distance here is 2 inches divided by 12 inches per foot, right? So this ends up being 210 over seconds. That's the units. So the a sub x then is u du dx is equal to 22.5 feet per second multiplied by 210 over seconds, and this equals 4,730 feet per second squared. And if you divide through by gravity being 32.2, this is basically 147 Gs. And that's a lot of acceleration. But anyway, so this is an idea of how we can actually get a non-zero value of acceleration for a steady flow case because the velocity can change as a function of space. And what's forcing that is this nozzle constricting the flow. Okay. We're going to change gears a little bit here. I'm going to move away from discussions about the Eulerian versus Lagrangian for the moment. In order for us to continue, again, our goal here is to come up with a way of describing the equations of motion as we know them, F equals ma, Newton's second law, all that kind of stuff, in a format that is useful for fluids. Again, those laws have been established for particles. Now we need to establish them for fluids using an Eulerian point of view, and so we need to make some changes to what those equations look like. So one way of changing those equations is via this convective acceleration. Another way is by translating between control volumes and systems. And so what we have to do here is offer something of a way of translating from a system to a control volume. But first, what we have to do is define all of that. And I apologize for my voice. The cold seems to have abated, but it's left behind this. My voice kind of sounds like I'm gargling nails, so I apologize for that. Um, so, control volumes and systems. Okay, so a system, by definition, is a collection of material with a fixed identity. Okay. Now, with the system, you can apply the laws of physics to a system. So, as an example, again, we'll talk about my favorite pastime, baseball. Baseball is a really good example of a system, right? It is a collection of material that has a fixed identity. We identify that, despite my sloppy drawing, we identify that as a baseball, right? And we know that the baseball has not only it's a fixed collection of material, right? It has a boundary. We know what is baseball versus what is not baseball by looking at this. Anything outside that circle is not a baseball. Anything within it is a baseball. All that material has an identified fixed identity. So, in this sense, we can apply the laws of physics to a baseball. We know back from our um, physics class what the equations for you know equations of motion for a baseball flying through the air might be. We know what forces act on it, all of that kind of stuff. So, in this sense, the system but we only know it because we're able to follow the baseball around. We're able to follow systems. systems can be easily followed and tracked. And that by virtue of that, the laws of physics can be applied to that because we know what the system is composed of. Um, so you can follow the system around, right? Now, this is difficult for fluids. Okay. Because if we wanted to follow a fluid in the same way that we would follow something like a baseball, we would have to look at it at a molecular level. That is, we would have to identify a molecule and follow that molecule around. Now, this is a little bit of an overstatement because, as I mentioned before, there are computational models that treat the fluid as Lagrangian particle aspect. So you can actually follow particles of fluid around. So it isn't really the reduction to a molecular level isn't really 100% necessary, but you do need to reduce it to something really small and identifiable. So in a sense, for applications that we would run into in a class, this is really impractical. So we need to find a different way of describing and manipulating our understanding, or not understanding, but the laws of physics that apply to fluids in a way that that keeps us from having to bring it down to a system. So what we want to do is we want to shift to a control volume. So with a control volume, rather than simply following a particle around, you basically have a volume in which you are looking at things going in and looking at things leaving. And then you recast the laws of physics so that it applies to that kind of situation. So control volume by definition is a volume in space through which mass enters accumulates. Let me move to another line here. And exits. This is closer to an Eulerian viewpoint. While a control volume can certainly move, there's no, if it were stationary, which is how we would typically use it, it is exactly the Eulerian viewpoint. Control volume stays put, things go in, things build up or deplete, things leave, and we just track that the comings and goings of the fluid inside from the control volume. So, but in general, control volumes can do a lot of things. It can be stationary. It can move, and they can deform. So long as you know the speed at which the control volume is moving, or you know the rate at which the control volume is deforming, that is, the surface of the control volume is either contracting or expanding, um, we're all good. We can apply everything that we're learning here to those types of situations. All right. So again, to state this, the physical laws that we know, they're written for systems. So we need to translate that to control volumes. Okay. And this is done via a device known as the Reynolds Transport Theorem. That's what this thing does. All right, so eventually at the culmination of chapter 4, we'll run into the Reynolds Transport Theorem, and then we will be able to rewrite the Newton's second law, for example, to apply to fluids via the Reynolds Transport Theorem. So what I'm going to do here, oh yeah, so let me move on to that here. Yeah. All right, I took advantage of my spring break prerogative by getting another cup of coffee here. So there's a slight pause. Okay, so now that I've introduced both systems and control volumes, let's compare and contrast the two and show an example why a control volume approach is um, far easier for fluids. Right, so let's say, okay, so first let's take a look at a system approach. And we'll show an example here. Let's say, again, you've got a baseball and you are basically throwing it at somebody, and unfortunately, that somebody didn't catch it. And so then it bounces off that somebody, and that person ends up doing something fortunate, like collapsing, that kind of thing. All right. This is really well suited for our physical laws because we have a system here that has velocity, has momentum, and then when it encounters this person, it has a change of momentum, which we can describe. There's an impact. We can describe that as well. So everything's describable um, via our physical laws. right? And the system is always well defined. Right? The system is the baseball. The impact is a change in momentum that happens to that system, and so on. And we can describe all of that. Now, let's take another example, and we'll say would also be a systems approach. But this time, rather than a baseball, we use a water balloon. Okay, so now we've got this water balloon. You'll have to take my word that this is a water balloon. This is a system. It's identifiable. You create a water balloon, you tie off the knot. It is a system. It's a easily identifiable, excuse me, collection of material with a fixed identity. It has a water balloon, and it goes through space as a water balloon. Deforms a little bit just due to interaction with the air, and then you find its target, and there is an explosion, of course, right? So the water balloon ends up exploding on this person. And there's a law that describes this impact, maybe F equals ma or something like that. But the thing is that's different now is the fact that now the collective identity of the system is now dispersed. Because now you've got water particles all over the place, right? And there's water here, water there, water there, water there, water there. And each of these has a law associated with it. Right. Maybe there's even a unfortunate bystander over here, way in the corner, who didn't expect anything, and now that person's full of dripping wet with system, that kind of thing. So, in order for you to be able to accurately determine, for example, the change in momentum that had to happen to this primary target due to this water balloon, which originated as a system, you actually have to account for all the water that made up that system. Okay. So if you're missing any water, if you're not accounting for it, it's lost due to some, it's a it hits that person, it explodes, there's water all over the place. Technically, you can't get an accurate read of the force that that person was hit with the water balloon unless you account for every drop of water that was originally in that water balloon. So clearly, this is not a very tenable way to treat fluid flow problems, right? So instead of doing that, we can do a control volume. Let me put a point on this. Excuse me. All right. Okay, so then what we'll do then is instead we'll try a control volume approach. So this time we'll take our unfortunate target right here and we'll enclose them with a control volume. Right. Okay. So sometimes we shorten this to read CV. Okay. Um, so what happens then is that we can remove this person and we can basically just translate this, convert this from something where you're actually looking at every nook and cranny of your target and trying to figure out where the water went to simply having a simplified volume in which you're just tracking what's going in, what's accumulating, and what's leaving. Something like that. Okay. So here's your control volume. Now, when you're looking at things coming in, like the water balloon, now you're only worried about things leaving and coming into this volume or whatever. So basically, you're only tracking what's coming in, what's accumulating or depleting inside the control volume, and what's leaving the control volume. And the nice thing about that is once you deal with the material that's entering through the control surface into the control volume, accumulating inside of it and then exiting it, you don't care about it anymore, right? So you don't necessarily anything that's leaving, you don't necessarily have to worry that it might be, in this case, maybe splashing someone else with that same water, and now that water needs to be tracked. You don't have to care about that anymore. You're only worried about what's happening through the boundaries of the control volume and inside the boundaries of control volume. Okay. All right. So I mentioned that there's also the possibility of having a moving control volume. That is also possible. In this case, we have our, let me move this down here. So in this case, our poor unfortunate target sees what's going on and starts to run. But you can still enclose that person in a control volume, you know, and this time the control volume is moving with a velocity v to track the in accord with the speed of your target. So this can now be converted into something that looks like that, same control volume shape, but it's moving at a velocity v. Okay, this time. Note that that velocity is not necessarily related to the velocity of the material going in or leaving the control volume. That's a separate thing. This is just the velocity solely associated with the control volume. Again, not related to velocity of material entering and exiting the control volume. Okay. Right. You can also have a deforming control volume. So you might be a situation like this. Sees what's going on and rather than running, basically decides to take a more defensive posture and just kind of hide. It's supposed to be somebody, it's okay. It's supposed to be somebody crouching on the floor. And so the control volume around that person is deformed to account for this change in posture, right? So now, so the control volume deforms around this person who's now adopting more of a defensive posture rather than running away, right? But we still have to account for things. What do we have to account for this time? This time we need to account for the overall change in the surface area and the volume of the control volume. Okay. So you have to account for that. But again, that is solely due to the control volume. It has nothing to do with the fluid or the material entering or exiting the control volume. It only has to do with the surfaces of the control volume, how it might change due to this deformation. The same way that in this case, the velocity that's involved is only the velocity of the control volume, has nothing to do with the velocity of the material entering or leaving the control volume, right? So that makes it very convenient, actually. So now we only have to worry about what's going on in this volume and do a bookkeeping accounting of what's happening inside, rather than necessarily worrying about what's leaving or what's leaving or accumulating or depleting, you know, elsewhere in areas that we can't necessarily track. All right, so that is a basic synopsis of the differences between a control volume and a control surface. I'm sorry, in a system approach. So what I'm going to do is head towards the Reynolds Transport Theorem. We may not get to it in this video lecture, which is fine, but we'll at least set it up because we have to do a few things first before we actually knuckle down and show where the Reynolds Transport Theorem comes from. We have to make a little bit of intro information here. Okay. So basically, it's a useful tool to translate from a systems approach to a control volume approach. Okay. So in order for us to do that, we have to define a few things. We have to define the difference between an extensive property and an intensive property. Okay. So what is an extensive property? It has to do with describing the material entering and exiting the control volume, right? That is the fluid or the momentum or whatever. So an extensive property is dependent on the amount of mass. Okay, so one example is kinetic energy. And because if you take a look at the expression for kinetic energy, it's essentially 1/2 mv squared. So you see m right here. So the amount of kinetic energy of something depends on its mass. Momentum is another one, because it's essentially the mass times the velocity. Weight, of course, is another. Mass times the acceleration due to gravity, and also mass itself. It's dependent on mass, etc. So these are extensive properties. Intensive properties, on the other hand, are independent of the amount of mass. So what are some examples of that? Density is a good example. Density because it's mass per unit volume, right? So um, right. Another one is a specific weight. They're also independent of the amount of mass. Right? So it's per something. So as an example, if you could, the idea being that if you could divide out the mass, then what's left is the intensive property. So essentially, in general form, we can write something like this, where this capital B is some extensive property, and you divide out mass, and what's left is the intensive property. And we'll use capital B and lowercase b to divide between extensive and intensive property, or distinguish between extensive and intensive properties. So if we wanted to take a look at the amount of extensive properties of a system, we can write it like this. Something that's integrated over the system, the mass density multiplied by that intensive property multiplied by the volume, right? So density times volume is mass, and so that multiplied by the intensive property is the extensive property. And this is then integrated over a system. So again, in the case of a baseball, um, the density of the baseball is divided out. What's left of the baseball is the intensive property, which per unit mass would be 1. And then you integrate over the system, which is the baseball, and you get the extensive property of the mass of the baseball. All right, so most laws are written in terms of a system. All right, so that would be something that looks like change of a extensive property of the system with respect to time is equal to d integrated over the system of the intensive property as a function of time. Right? So like that. But what we really want is to convert this to control volume. So in other words, do this. The volume. So something like that, right? Problem is the conversion is not straightforward, and going from this equation here to this equation here requires the Reynolds Transport Theorem. Okay. So, so okay, so let's see. Hang on. So again, we're to highlight, we just use another example to highlight the differences between systems and control volumes. Something is, sorry, I've got a notification bothering me here. Oh, okay. Um, so let's say we take a look at a fire extinguisher. And I'll draw it as a bottle like that. Okay. And then we can identify the outer surface um, of the fire extinguisher as a control volume. And then we can list the material inside this control volume as a system. Okay. So um, when nothing is happening at time t is equal to 0, the control volume and the system are essentially the same thing. But it is not the most, it is probably the most trivial case. Nothing's happening, right? So now at this point, it's time to fight the fire, and now you open the valve. Now you've got going through here, you still have a certain amount of system inside the control volume, but now all this stuff is coming out. And all this can be also comprising the system. So that's your system. This is also part of the system, but the control volume is still the same. Right? So the thing is that within the context of the system, the mass of the system is unchanged. Whether you are keeping that foam within the original bottle or tank, or opening the valve to put out the fire, the amount of system, which is the mass of the system, the mass of the foam, remains unchanged. So the mass of the system remains unchanged because as long as we're able to track where the foam goes, we can account for it all, right? Thing is, though, is that now we no longer have this equivalence between what's going on in the system, what's going on in the control volume, because now the mass inside the control volume is reduced. That changes. So what I'm going to do is take a little bit of a breather to then move on to the next section while I get my notes ready for that, and I'll rejoin. I'll restart the recording shortly. Okay, so what I'm going to do now is I'm going to talk about the actual Reynolds Transport Theorem, finally. Here. And we're going to do it for the case of a single one inflow and one outflow, a simplified case. Hey, buddies. The dogs just walked in. one inlet and one outlet from the control volume. We'll look at a general case next time. Now let me get through this one. And this will kind of set it, this will give us a very fun, like I said, simplified understanding. And but we'll look at the more general case will be one that we can adopt for um, solving problems. Okay, so let's take a look at a situation where we have a boundary that is slowly closing in, like something like that. So this is a boundary that's containing a flow, right? And what I'm going to do is I'm going to identify a system here. So fluid has been flowing through this cavity for forever, right? But coming out through here at V2 and going in here at V1, that there's this boundary here. The inflow we'll call 1 and the outflow we'll call 2. Like that. Okay. And this we'll call a time t. Some arbitrary time. This is a situation. Now the control volume is the pipe or the domain between 1 and 2. We'll call this a pipe. So it's a pipe between 1 and 2. Remember that a control volume is stationary and we're only looking at things going in and out. So it makes sense for the control volume here to be the pipe, the thing that contains whatever we're looking at. And what we're looking at is the system. The system, on the other hand, is the fluid that occupies the control volume at time t. So the control volume is in the solid line and the system is in the dashed line. Okay, now I'm going to do something a little bit mean. I'm going to take this, I'm going to go ahead and copy this. And move it down over here. Okay, so now we're looking at a situation where at time t plus delta t. So there's been some change in time. We've moved forward. The control volume stays the same, but the system has moved. The fluid moves. So in this case, what is the system now? The system is still the same collection of material that was there at time, that was identified at time t. It's just that now that whole system of material has moved from right to left, right? So I'm going to draw in purple what the system now looks like at time t is equal to t. Let me do this first. A blue, and then a purple. So now at purple, what we're seeing is the collection of material that makes up the system at time t is equal to time t plus delta t. All right. And so uh, on the left, that system has moved a distance L1. And on the right, it's moved a distance L2. Right? Okay. So L1, the distance is equal to the velocity V1 multiplied by delta t, right? It is the amount, the distance is the velocity multiplied by the increment of time. So that distance here, L1, is equal to V1 times delta t. And conversely, well, I'll just do it in blue. L2 is equal to V2 times delta t. Okay. So what we're going to do is we're going to take this, the collection of dashed lines, and we're going to get it out of the pipe for now. Okay. So again, our oh, shoot, that. Right. So there would be the system at t, and then we'll go ahead and draw the system at delta t. Let me. No, that's okay. So that's kind of what we've got. We've got this distance of L1, and we've got this distance L2, right? So we're going to, and this is originally 0.1, and that's originally 0.2. That's denoting the upstream and downstream ends of the control volume. Those stay the same. So what we've got though is a couple of three different regions that we can identify. We'll call this region here 1. We'll call this region here 2. And we'll call the region that remains the control volume -1, right? Because that is, oops, oh, sorry, buddy. That is the region that was originally the control volume. Then over the course of delta t, it lost the region 1. Okay. So over delta t, for delta t, the system moved out of sorry, out of 1 and into 2. Okay. So at t, the system, come on, man, sorry, is equal to the control volume. At t plus delta t, the system is equal to the control volume minus region 1 and plus region 2, right? That's the stuff that's in purple. So if we wanted, what we want to do here is track the extensive property, capital B, of the system. So again, doing that, it means that T, whatever this material is, B, the property is, B system of the amount of B in the system is equal to the amount of B in the control volume at time T, right? And at T plus delta T, it changes the amount of B in the system at T plus delta T. Thank goodness, writing gets really bad. Is equal to, oops, what is that? Control volume of is B of the control volume at T plus delta T minus the amount of B in region I, or 1, at T plus delta T, plus the amount of B in region 2 at T plus delta T. Right? Okay, this makes sense. And so what we want to do is take a look at the change in the system, of the B of the system over time. So that would be delta B system over delta T is going to be equal to B of the system, T plus delta T, minus B of the system, T, divided by delta T, right? Which equals, we substitute in what we have up here, what we get is B of the control volume. So now we're able to write this in terms of control volume. T plus delta T minus B in region 1 at T plus delta T plus B in region 2 at T plus delta T minus B of the system at point T over delta T. So basically what we did, excuse me, is we took this and converted it to something that relates to a control volume, which is all this, right? But also, this B system at T is what? Remember that at point T, when nothing's happened yet, or things have been happening, but we're starting our observation, the system is equal to the control volume. So this is actually equal to B in the control volume at time T. Okay. So let's take all this and break it up. Delta B of the system divided by delta T is equal to B of the control volume, T plus delta. Sorry, my writing is getting really bad. I think my eyes are, hang on. Oh, here you go. Get a pair of, get my trusty readers on. Here we go. Okay, so control volume, T plus delta T minus B in the control volume, T divided by delta T minus B in region 1, T plus delta T over delta T plus B in region 2. Shoot. Do it over here. B in region 2, T plus delta T, happening over the time frame delta T. Okay, so we'll call this term 1, we'll call this term 2, call this term 3, we'll call this term 4. And we'll take a look at each one of these. Now, at the limit, at t sorry, I meant delta t approaching 0, term 1 converts from this to this. So finite differences become actual differentials as delta t goes to 0. Term 2 goes from b over the control volume at t plus delta t minus b over the control volume at t divided by delta t. That's going to become db over the control volume delta t. Or if we write it in terms of the intensive property, we end up with something that looks like this. Right? Where we recognize, oops, sorry, maybe more like this. We recognize that B is equal to mass times small b, right? So the integral from density over the volume is the mass, and then the intensive property is B. So that will allow that whole thing to become capital B, the extensive property. All right. We've got about a minute to go, and I don't think I'm going to finish. So what I'm going to do here is stop. Then we'll treat terms 3 and 4 in class on Thursday, and then we will do the, that will give us the Reynolds Transport Theorem for a simplified situation. And then we'll look at a more complicated or general situation, which won't take a whole lot of time, but we'll recast the Reynolds Transport Theorem a little bit, and we'll have our quiz. All right, the quiz will be about the homework that's due. So see you in class.